Good day everyone. This is Pradeep Dayanandam. Today I am presenting my thesis Sarcasm Detection in Amazon Product Reviews using Common Sense. The presentation today will be structured in the following 6 subsections. First we will be going through the introduction where we will be talking at a high level about NLP, sentiment analysis and sarcasm detection. We will also discuss the background and the motivation behind our research. Next we will be going through the literature review where we will touch upon the multiple kinds of research done in this field. Then we will be talking about the research methodology where we will be going through the approach that will be taken to address the problem statement. Next, we will be going over the implementation and execution plan of how we will be bringing our methodology to life. Then we will be talking about the results, have a discussion and critical analysis of the results achieved. Finally, we conclude the thesis with future recommendations. Now, what is sentiment analysis? Sentiment analysis is the process of detecting positive or negative sentiment in a text. It is often used by businesses to detect sentiment in social data, to measure brand reputation, and to understand customers. From a machine learning perspective, sentiment analysis comes under the broad category of NLP, that is natural language processing, and further comes under NLU, natural language understanding. NLP is a field in machine learning that deals with the ability of a computer to understand, analyze, manipulate, and potentially generate human language. Sentiment analysis is one of the higher degree tasks in NLP. Now, sarcasm detection. It is one of the critical subtasks under sentiment analysis. The goal of sarcasm detection is to determine whether a sentence is sarcastic or not. As per Merriam-Webster dictionary, sarcasm is defined as a sharp utterance designed to give a cut or pain. In simple terms, sarcasm is nothing but words that imply the reverse of what they say with the intention of hurting someone's emotions or humorously criticizing something. While the definition might seem obvious, in reality, detecting sarcasm is a challenging task since it is heavily reliant on context, past information, and the tone in which the line was stated or written. Sarcasm detection is used in wide range of NLP applications, including marketing research, opinion mining, and information classification. Let us now delve into the what and why of our research. There have been multiple researches done in the past using various techniques to detect sarcasm. But our study is specific to the detection of sarcasm in Amazon product reviews by using the common sense knowledge. This is the key problem statement that we are trying to address through our research. Our aim and objective are also in line with the problem statement that we had just mentioned. The primary research question that we are trying to address is, does the use of common sense knowledge help in detecting sarcasm in Amazon product reviews? In the current context, a consumer's perception of a product and the subsequent recommendation of similar products to the consumer is heavily influenced by their reviews. If the sarcasm in the review is misunderstood, it might have a detrimental impact on the customer experience and thereby leading to customer churning. Let us now move into the literature review section. Sarcasm detection has been studied as a problem statement in various domains, including psychology, linguistic studies, and cognitive science. Broadly, we can try to classify sarcasm detection into rule-based approach, classic machine learning algorithms, deep learning models, and pre-trained language models. The rule-based approach and classic machine learning algorithms are grouped as early approaches in our review for convenience. The rule-based approach can be either lexical method, syntactic method, or semantic methods. The lexical method can further be either corpus-based or dictionary-based. In our literature review, we have not discussed a lot about the rule-based approach as we have focused more on the machine learning approaches. At the heart of it, sarcasm detection is simply a classification problem once the required data pre-processing is done. Hence, most of the classic machine learning algorithms have been extensively used by various researchers. Some of them include support vector machines, logistic regression, k-nearest neighbors, decision tree, random forest, naive Bayes, and so on. Either these algorithms are used standalone or in an ensemble model or in combination with few other rule-based approaches. Next comes the deep learning models. From the usage of simple artificial neural network models such as a multi-layer perceptron to using convolutional neural networks and recurrent neural networks such as long short-term memory, gated recurrent unit and bidirectional LSTM, researchers have explored most of them. Finally, with the advent of transformers-based models and subsequently with the dawn of pre-trained language models such as BERT, GPT, etc., researchers have shifted their focus on fine-tuning the pre-trained language models to the particular task at hand. Using pre-trained model gives fast and more accurate results in short span of time, while also leaving very little carbon footprint. During the literature review, we had observed that the sarcasm detection in Amazon product review is rather an underexplored area. Now, this could probably be due to the unavailability of a large data set. Most of the sarcasm detection researches are carried out in social media data sets such as Twitter or Reddit. While Amazon provides a huge review corpus, this does not necessarily come labeled for sarcasm. So hence researchers on this dataset are either unsupervised researchers or semi-supervised. The next observation that we noted was regarding the use of common sense in sarcasm detection. The use of common sense in natural language tasks such as story generation, question and answering, natural language inference, sentence classification, and so on has been there in existence for a long time. But use of common sense information in sarcasm detection is another underexplored area. In our study, we wanted to merge both the above studies and try to bridge the gap. Generally, any kind of review data is quite different from a social media data because in a way that it is specifically intends to appreciate or criticize a product or a service. Hence, this is going to be a challenging task at hand. Here we can see the high level flow of our entire model. We will be using the Amazon customer review corpus curated by Elena Filatova. The sarcastic and the regular reviews, which are independent files for each review, are passed to a data transformation block. You can see here. This data transformation block contains the code required to extract the review text from the corpus, label them, and store them in a JSON list file containing the text data and corresponding label. There is no particular constraint that the resultant data should be stored in JSON format. It is just a convenient format for us to process. This data file is then split as train and test data. The split data is then passed on to this pre-trained language model. Once the training is completed, the model is tested on test data and the results are displayed. In the second flow here, we can see that the transformed data is being sent to a common sense transformer block. The output of this block is another JSON file which now has the text data, corresponding label, and in addition common sense information. This common sense infused data is again split into test and train data, and then it passed to a pre-trained language model for training again. And once the training is completed, the model is again validated on the test data and the results are displayed. Now here comes the third flow where a graph convolutional network is introduced. While the pre-trained language model in the previous step is independently used in predicting whether the common sense infused data is sarcastic or not, in the process it performs sentence embedding for each text. These embedded sentences can be used as graph embeddings. These are then passed on to the graph convolutional network, that is the GCN model, which produces a node embedding vector. This is then passed to a feed-forward neural network with a softmax activation function for classification. Now, before we go into detail, let us first take a quick look at what is Comet and what is GCN. Now, we have been constantly using this terminology common sense throughout our study, but what do we actually mean by this common sense? Generally, most of the NLP tasks involve training a model with a large amount of text data. Now, this text data is usually a large data set from various sources of different domains. Hence, it is natural that this text data contains some level of worldly common sense knowledge which can be tapped to improve the performance of any NLP model. But how can we extract this common sense knowledge? So this was explored in detail by Boslet in their study, where they introduced a new architecture called the Common Sense Transformer, in short COMET. Now, COMET is a transformer-based architecture which can extract common sense information in the form of various descriptors such as X want, X effect, X intent, X need, X react, and so on. So for our study, we will be using only the X want and X effect as they capture most of the information that we would need. We will be using a pre-trained COMET model from the official source provided by the researchers without any modification to the code. In the provided example, we can see for the given input, the common sense descriptors are extracted as X want and X effect. Now, X want is simply like what does the person X wanted by doing this action. So, and X effect, by doing that action, what was the effect on that person X. Now, we can represent this information in the form of nodes and edges as shown here. This graph embedding is then made use by the subsequent GCN model. Now, GCN is a type of a neural network which can be considered as an approach to generalized convolutional neural networks to the case of graph structured data. Now, graphical data naturally arise in many real-world applications like social media analysis, relationship maps, and knowledge banks, where the information is captured in the form of nodes and edges. GCN can be used in number of tasks such as graph classification, node classification, link prediction, community detection, graph embedding, graph generation, and so on. Our usage of GCN corresponds to the graph classification task. Let's quickly touch upon the evaluation metrics that we will be using. First, let us try to understand the confusion matrix. So, in a classification problem, the predicted values can be one of these four metrics mentioned here. The true positive is when the observation is positive and it is truly predicted as positive, and false negative is when the observation is positive but it is falsely predicted as negative. And similarly, like false positive is the observation is actually negative but it is incorrectly predicted as positive. And similarly, true negative is when the observation is negative and it is truly predicted as negative. Now, using this, the precision, recall, F1, accuracy are all calculated. Precision measures how precise our model is in detecting the in predicting the positives. It gives a view as to how many of the predictive positives are actual positives. The precision is a good measure when we want to keep false positive as low as possible. And similarly, recall gives a view as to how many of the total actual positives are correctly predicted as positives. Recall is good when we want to keep the false negative as low as possible. Now, in a real world scenario, we would use something like an F1 score. F1 score is a balanced measure between precision and recall. This is most commonly used because it generally keeps that balance between false positive and false negatives. Mathematically, the F1 score is the harmonic mean of precision and recall. Accuracy is the ratio of total correct predictions out of all the values. For our study, we will be mostly focusing on the F1 score. The data set that we will be using is Amazon Customer Review Corpus, which is curated by Elena Filatova. There are about 817 regular review files and 437 sarcastic review files in an XML-like format. So each file contains a single review for a product. A sample file is displayed here. You can see that besides the review, which falls under the review tag, there are other information like stars, title, date, author, and product. But for our study, we will be using only the review data. Here you can see the first major block in our architecture is the data transformation block. So in this, each of the sarcastic and non-sarcastic review files are passed through a piece of code which first initializes a dictionary of lists. Next, there is a code which extracts data from the review tags. This extracted data is then passed through another function which will clean the text by removing any additional space or unrecognized characters. Eventually, this extracted and cleaned data for each review is appended to the dictionary of lists that we initialized earlier, and eventually it will be saved as a JSON list file. This JSON file will be subsequently sent across to the the baseline model and the comment model thereon. For our baseline model, we will be using 3 pre-trained language models for this study. They are BERT, Roberta, and DistilBERT. We will be using the Hugging Face Transformers framework to import the required pre-trained language models. The transformed dataset containing the text data and the label in the form of this JSON list file is fed to the pre-trained language model. The provided text then undergoes a process of tokenization, sequence embedding, and adding attention mask. Further, the data is then split into train and test data by random splitting. This training data set is then passed on to our the language model, where the training is completed and the test data is used for validation. Once the results are captured, the evaluation metrics are calculated independently by using both inbuilt functions and custom functions that we have written as well. Next, you can see here that next model is the common sense infused model. For this, we will be making use of the common sense transformers, which was discussed earlier. As stated earlier, we will be using the official implementation of the Comet model without any change to the code. So from the JSON list file, which has both text data and the label, we will pass the text data alone to the Comet model. Now the model will then produce output for multiple common sense descriptors. We will be using only the XWant and XEffect common sense information. These common sense descriptors are used as a support and appended along with the actual text data during the tokenization process. The subsequent pre-trained language model uses this common sense embedded data to predict whether the review data is sarcastic or not. Now the third model that we will be using is the GCN based model. This model is based on the graph convolutional network, which we discussed earlier. In the previous Comet based model, we had the pre-trained language model for embedding common sense data during the tokenization process. Now that same common sense embedded data is passed down to this GCN model as input. This data contains the initial graph embeddings, which are used by the GCN model to create node embeddings as a vector. This is then passed on to a feed-forward neural network with a softmax activation function to classify whether the data is sarcastic or not. Let's move on to the results. Once the models are built, we conduct a series of experiments with varying configuration settings and different hyperparameters. For each language model, there are quite a few hyperparameters like learning rate, batch size, optimizer, and number of epochs, etc. They need to be tuned at different stages for all the models being used. After performing a series of experiments, the best results for each model is displayed here. From the results, we can clearly see that the common sense infused model is performing better than the baseline model. While comparing the baseline model and the common sense infused model, there is almost 6% increase in the F1 score across all 3 pre-trained language models, which is considered a better result. While there is a significant improvement in the GCN based model as compared to the baseline model, when Comet based model is compared, this is almost on par with each other. Overall, all of these results that we are seeing right now are considerably better than the classic machine learning algorithms like SVM and logistic regression. Also, we can see that irrespective of the type of language model chosen, whether it is BERT, Roberta, or DistilBERT, the results are pretty similar. This is primarily due to the fact that underneath all these models, they have a very similar architecture and perform similar kinds of encoding. And also of these 3 language models, what we noticed is that DistilBERT is the fastest, and rightly so. It is 60% lighter than the bird version. Let us now try to do a critical analysis of our study. Our studies have shown that there is a 6% increase in the F1 score between the baseline and the common sense infused model. Though it is a better in number and it is a good increase, it is not quite significant enough considering the data set of the size of the data set that we are used in our research. And also we have not been able to explain why there is an increase in the F1 score between the baseline and common sense infused model. There are methods using saliency test and saliency maps where we can try to understand why the model has taken such a decision, but we haven't been able to explore it a lot. And also one could argue that the volume of the dataset is not quite large enough for the study to be generalized to other datasets. However, the scope of our study was well defined right at the beginning, that it is limited to this specified dataset, in which we can clearly see that the increase in F1 score. With this, we can definitely consider that our primary research question has been answered, and thereby we are inching towards the right direction. Let's move on to future recommendation. The use of common sense knowledge in sarcasm generation is at a very nascent stage, but has a huge prospect. This field can be explored further to develop hyper-realistic conversational AI. There is a general shortage of labeled dataset for sarcasm detection in the reviews space. So we could possibly come up with an unsupervised or semi-supervised model in conjugation with our model, which can improve the accuracy of the prediction, and thereby it can be used for dataset labeling. We can also extend this study further to a different dataset and find out whether the common sense knowledge can be applied everywhere. We can also see whether we can make use of the XWant and besides XWant and X effect, are there any other common sense descriptors that we can make use and try to predict whether the sentence is sarcastic or not. We can also explore more on the saliency test and saliency maps to improve the interpretability of the model. This could be a worthy area to explore further and would prove to be a step taken in the direction of building explainable machine learning models. Finally, the primary aim of this research was to develop a model which makes use of common sense information in the identification of sarcasm in a particularly Amazon product reviews dataset. At the end of the research, we can say that we have been able to achieve the aim and objectives that we set up for ourselves within the scope of this study. We have also been able to address the associated research questions which we set up early in the beginning. Along the way, we have also discussed about the gaps that are there and also what are the future way forward that we can take it further. With this, I thank you for your time and for providing me this opportunity. Thank you once again.